तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, we discussed about this common emitter amplifier. Today, let us look at the complete picture of the amplifier. This RE and RC resistors have been introduced in order to do the biasing for the transistor. RE is going to fix up the current IEQ so that irrespective of the transistor that is used, the operating current remains as fixed by you. Then RC is fixed for a given VCC for the required VCB, okay, reverse bias. So that is the operating point, a certain IE flowing with certain VCB, okay, will fix the transistor in the active region of interest to you, so that you can use it as an amplifier. Now, when this happens, let us see what exactly happens at any instant of time. So, we are now going to consider the effect at any given instant of time of applying a signal. So, we have here current that has been fixed for the transistor as IEQ, the quiescent DC current. I have told you that capital I with suffix capital indicates DC. Right. So, corresponding to which we have alpha times IEQ flowing here, okay, which is ICQ. Strictly speaking, alpha times IEQ plus IC naught. We have ignored IC naught. Okay. So, ICQ, which is very nearly equal to IEQ, alpha being close to 1. Corresponding to which we have the base current getting fixed as, okay, IBQ. So, we have here this relationship, of course, IEQ into alpha is equal to ICQ, IBQ is equal to IEQ by beta plus 1, and this relationship getting satisfied, and IEQ is going to be very nearly equal to VEE minus V gamma divided by V gamma being equal to typically 0.6 volts. So, this is what we had biased the transistor at. The voltages VCC minus ICQ RC is equal to VC, okay, with respect to ground, and VB VCQ we will put it, VBQ is very nearly 0. This is what we said, because it is equal to IBQ into RS with a negative sign, minus IBQ into RS. And for most of the reasonable values of source resistance, this minus IBQ into RS can be ignored. So it is very small, or it is actually IEQ RS by beta plus 1. Okay. Beta being very high and most of the drop occurring across RE, we can ignore this. Okay. So that is under the assumption that RS divided by beta plus 1 is much less than RE. Okay. So this is a proper way of biasing a common emitter amplifier circuit. This is what we had discussed so far. Now let us superimpose over this. Because of Vs, okay, there will be a change in current. Let us say it is plus here minus here, indicating that the voltage is increasing. Delta Vs, okay, is positive here. Okay. So please remember, small letters with suffix also small indicates the time variation in signal. Okay. The small letters with capital suffix indicate the instantaneous value of, okay, the signal at any, including DC as well as AC. Right. So this is the variation Vs. For this variation, there is going to be this is going to increment the base emitter voltage. So current is, base current is going to increase because emitter current increases, base current also increases. This polarity, the base current is increasing, okay, in this direction. That means IBQ plus, we will put it as delta IS, that is what we have been using, or we can indicate it as only signal IS, right. So this is equal to IB, instantaneous value of IB. Because of this increase, okay, and in this case the incremental value of signal current, okay, is also the same as the incremental value of base current, because, okay, this change in signal current is the same as I, okay, B. So this is 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 equal to IB here. So this is actually equal to IBQ plus IB, because IB is equal to IS. Is this understood? These symbols and things like that. Okay. Now when this happens, what will happen here? IEQ will be IEQ plus, okay, the change that has been brought about, that is I small e, which is really the I instantaneous value, I. So for a change in signal voltage here, because base to emitter current voltage increases, correspondingly emitter current increases, the base current increases. You can think of it that way. Then corresponding to this, we will have, okay, a change in collector current, which will result in the instantaneous value. All these can be assumed to be, okay, linear relationship, that is that ICQ equal to alpha times IEQ is valid, and delta ICQ is equal to alpha times delta IEQ is valid, okay, assuming the alpha AC is very nearly the same as alpha DC, right. Then the change, for change in signal also the same relationship is valid. Okay. So we have all these relationships related by the same factor alpha as far as the emitter current is concerned. Collector current is related to emitter current whether it is DC or incremental by the relationship alpha, assuming alpha for DC is the same as alpha for the changes. Then we know that when the signal, let us say, is a nice sinusoid, let us say, this is the signal. So, we will call this say Vp sin omega t. Vs is a time varying signal, periodic. This is normally the test signal for testing any amplifier, okay, because any periodic signal can be broken up into summation of fundamental and its harmonics. So, okay, we can therefore test any of your amplifier by using a sinusoid as the test signal. So, if Vs is Vp sin omega t, then if the base T emitter change is very small, the change in voltage is very small, corresponding to which there is going to be a change in emitter current, that is delta VBE, okay, and delta IE, which have now been replaced by delta IE is replaced by IE small suffix e. Right. So, that is also going to be sinusoidal, even though this VBE and IE are related exponentially. We can say that as long as this delta VBE is small over and above the VBEQ, this is going to be at V DC VBEQ, which is 0.6, let us say, right, and this is going to change to VBEQ plus delta VBE or VBE. Right. Yes. If this change which is occurring over and above the quiescent, which is 0.6, is very small, kept small, then I can say that these two relationships, that is IE and VBE, are linearly related, and that linear relationship we have already established. What is it? VBE by IE is equal to VT divided by IEQ, which is nothing but actually delta VBE by delta IE, which we have earlier established. This is the direct relationship, okay, VT divided by IEQ, where VT is equal to 26 millivolts at room temperature. So, that means actually for a change in voltage here, there will be some change in voltage here, okay, and there will be a change in current in this, okay, structure, and the change in voltage and then change in current, they are linear if these changes are small, okay, linearly related by this relationship. Now, if that is not the case, then what we should do is that IEQ IE therefore is equal to, okay, IEQ plus this IE. And how do we determine this? We can assume that this change Vs, because we have put a capacitor here, okay, it is a short circuit for the signal, that is this, and therefore, this terminal is almost at the same potential as this, okay, as far as signal is concerned, and therefore, this potential is going to be very nearly at this, because we are neglecting the drop, okay, across this. Or we can just say that if this is Vs, there will be some drop here which is Is into Rs, I small s into Rs, and the rest of it is going to be dropped across. So, across the transistor, which is delta Vi or delta Vbe, which we have been calling it. So, we can therefore say that this potential is going to be delta Vi considering that this is the input to the amplifier, okay. This is grounded, this is delta Vi, is going to be same as delta Vbe is now Vbe, okay, according to our new terminology. Instead of putting all delta, we know that we are going to discuss this as time varying voltages, okay. So, if I have the relationship IE, this instantaneous value of emitter current is related to this, okay, IE naught reverse saturation current exponent into Vbe divided by Vt approximately, -1 is ignored. This is the diode relationship, okay. IE instantaneous value of current is nonlinearly related to this. So, if okay, this is this, then IE naught exponent Vbe by Vt can be written as exponent Vbe q by Vt plus Vbe by Vt, the time varying component, okay. And this is IE naught exponent Vbe q by Vt into exponent Vbe by Vt. This part is nothing but IE naught exponent Vbe q by Vt by definition is IEQ by definition, okay. This IEQ is already fixed by us, operating current, okay, into exponent Vbe by Vt. Vbe is the input voltage Vi. Right. So, in the common emitter configuration, right, Vi is the voltage that is applied between this and this, or this and ground, okay. So, if this is the amplifier, that is the voltage appearing at the input of the amplifier. To that voltage, okay, this current instantaneous value of emitter current is related in an exponential manner. So, this is the nonlinearity. So, if I make Rs equal to 0, let us say linearly, right, then make Vs equal to this Vp sin omega t this way, then this is going to be not really sinusoid, okay. It is IEQ exponent Vp by Vt sin omega t, totally nonlinear, okay. So, let us say this Rs equal to 0, assume Rs equal to 0, then Vi is equal to Vs, okay. Under that situation, you can say that this is equal to IEQ, okay, exponent what? Vp by Vt sin omega t. Now, this is equal to IEQ into exponent x, okay. When this quantity x is small, e to power x is 1 plus x plus x squared by factorial 2 plus x cubed by factorial 3. So, we expand that 1 plus x squared so on. This we had derived in the earlier situation also. Okay. This is what is wanted. Actually, if I want the instantaneous value of the emitter current to be linear with the input voltage, which is Vp sin omega t, linearly related, I want these factors to be very small compared to this factor. Okay. So, there is IE, okay, superimposed over IEQ, okay, plus IEQ by Vt into Vp sin omega t. This is the input voltage. Okay. So, this IEQ by Vt into Vp sin omega t, okay, is the factor of importance in an amplifier. It is linear. The other part is, let us, Vp squared by Vt squared into sin squared omega t can be expanded as 1 minus cos 2 omega t by 2. So, ignoring the other higher harmonic factors, right, because there will be factorial x squared by factorial 2 here, right, 2, and x cubed by factorial 3, which is 6, so on. So, that will be reducing. So, this 2 and this 2, okay, will result in, okay, the harmonics getting reduced as we. So, we have here an important piece of information. Okay. If we want this to be very small, okay, this factor Vp squared by 2 Vt squared, okay, dimensionless quantity should be very small, okay, compared to this here, okay, this into what? IEQ, because IEQ has been coming everywhere. Right? So, this is one way of testing the linearity. If an amplifier is biased at IEQ, right, when you apply a sine wave signal, pure sine wave signal, the bias point, DC point itself shifts, okay, and the amount by which it shifts gives you an idea about the distortion. This is what is unwanted. The second harmonic component was not there in the input. This has been created by the amplifier nonlinearity, and this is called distortion. So, a quick quantitative assessment of the distortion can be done by merely finding out the shift in the DC operating point of your amplifier. Is this understood? Because the shift in the DC operating point, which is corresponding to this, okay, by an extent which is earlier IEQ gets shifted to IEQ into Vp squared by 4 Vt squared. So, that will straight away give you an idea about Vp squared by 4 Vt squared, a measurement technique, simple measurement technique of what? Distortion. The extent of second harmonic distortion it is giving, okay. So, that is the predominant harmonic distortion in a common emitter amplifier. Please remember, therefore, a common emitter amplifier has predominant distortion, which is second harmonic distortion. So, the DC is IEQ into 1 plus Vp squared by 4 Vt squared, okay, plus IEQ by Vt into Vp sin omega t. So, this is getting transformed, this Vp sin omega t is going to be transformed by a transconductor factor, which is IEQ by Vt here. Okay. A change in input voltage, which is Vp sin omega t, becomes a change in emitter current by a factor which is IEQ by Vt. Okay. Vp sin omega t being the input voltage. So, IEQ by Vt is the transfer parameter factor. Okay. So, basically it is called transconductance. Right. Now, apart from this, we have minus IEQ Vp squared by 4 Vt squared cos 2 omega t. So, measuring this IEQ Vp squared by 4 Vt squared is going to give you the peak value of the second harmonic. A quick way of distortion factor assessment is this divided by what? This is the peak factor Vp IEQ into Vt of the fundamental. So, IEQ Vp by Vt, so percentage distortion or distortion factor is fundamental, okay, that is second harmonic, okay, this is the peak. RMS also is going to be proportional to the peak, okay, 1 over peak over root 2. So, ratio of the RMS value of the second harmonic, okay, divided by the fundamental will give you the distortion factor approximately, because we have ignored third harmonic onwards, right. So, Vt. So, how much is this? IEQ gets cancelled. So, it looks that the distortion factor is fairly independent of what? The operating point, right. So, we see here IEQ getting cancelled and it is equal to Vp divided by 4 Vt. It's an important thing. Quickly you can assess now the amount of distortion in a common emitter amplifier if your input voltage is given as, let us say 1 millivolt, let us say peak, Vp is given as 1 millivolt peak, 1 millivolt sin omega t, let us say, then this will be 1 by 4 into 26 millivolts. If you want for assessment, you can take Vt as 25. So, 1% distortion is what is going to be cost for a signal of 1 millivolt. So, we had just seen that when I apply a signal Vs equal to Vp sin omega t, and if Rs is 0, then IE is equal to this and IC is equal to alpha times IE, and V0 output voltage is going to be equal to VCC minus alpha times IC, that is alpha times IE, okay, or VCC minus IC times RC, which is alpha times IE times RC, okay, which is going to be VCC minus alpha IEQ RC into 1 plus this. So, this is the output voltage for a sine wave input which is Vp sin omega t. So, output voltage is exactly replica in shape of the input voltage, but by an amplification factor, okay, amplified only if these are negligible, otherwise it has other harmonic contents in it, therefore distortion factor. So, that we have made sure by making Vp much less than 4 Vt, an important design criteria, right. So, that all these factors do not disturb our operating point, okay, as well as do not cause any distortion, in which case we can neglect the effect of all these things and say that output is essentially this plus this. What is this? VCC minus alpha IEQ, which is ICQ. Alpha IEQ is equal to ICQ into RC, okay, is nothing but VCQ. VCC minus alpha IEQ is VCQ quiescent, okay, minus alpha IEQ by Vt into RC, okay, into Vp sin omega t. So, notice this, it is VCQ, that means this is VCQ, let us say this is VCQ, let us pictorially indicate, and if input is such that it is increasing like this Vp sin omega t, output will decrease. So, the minus, that means this voltage is decreasing and it will increase like this, VCQ minus, that is the significance of minus. Around VCQ, this is the quiescent voltage of the output, okay, around VCQ, and it because of input this is what is going to happen, and the extent to which it is going to be amplified is going to be Vp is its peak. Now, it is Vp into alpha IEQ by Vt into RC. This is called transconductance of the transistor, defined as Gm. Alpha IEQ by Vt is defined as Gm, transconductance. It is current divided by voltage, that is why it is called conductance. Transfer, because for an input change, okay, in signal Vi, there is going to be an output change in current, because of that it is arising, okay. Because of the output change in current and that change in current passing through RC, this, okay, amplification factor is arising. So, Gm into RC, okay, into Vp is the thing. So, Vp was the input and this factor is called the voltage amplification. So, please remember, in any amplifier, therefore, the voltage amplification factor is always equal to minus Gm into RC. Gm is, okay, defined as the transconductance. So, typically for example, for 1 milliampere of operating current, if Vt is 26 millivolts, 1 by 26, or we can take it as 1 by 25 for example, okay, is going to be 40 millisiemens, is a typical transconductance of a bipolar junction transistor for 1 milliampere operating current, okay. So, 1 milliampere divided by 26 millivolts, alpha is very nearly equal to 1. So, which is about what is it, 1 by 25 we will take. Okay. So, 40 millisiemens. Instead of calling millimos, we will call it millisiemens. Okay. So, for higher current, for example, it is 2 milliamperes, it will be 80 millisiemens. So, if you just know what the operating current is, you know the transconductance of your bipolar junction transistor. That is not the case with other active devices. Okay. The greatest advantage of bipolar junction transistor is you know most of its story the moment okay, you know the operating point. So, this is an important factor that you should remember, that the transconductance factor is immediately known the moment we know the operating current. And if you fix the collector resistance RC, then the amplification factor is also known. Okay. So, if RC is let us say 1 kilo ohm and operating current of the transistor is 1 milliampere, for which we are assuming that the transconductance is 40 millisiemens, the gain of the amplifier is minus 40, simple, voltage gain. Or suppose you are asked to design an amplifier with gain of 100, let us say minus 100, and you have fixed the operating point at 1 milliampere, for which the transconductance is 40 millisiemens, then the RC that you should select is 2.5 kilo ohms. Is this clear? So, designing a common emitter amplifier for a specific gain given the operating point or otherwise, right, becomes now very simple affair. How to fix RC, okay, how to fix the operating point given RC. These are going to be simple affairs. Okay. We can do it without any effort on your part, just by using this information that GM of a bipolar junction transistor is IEQ divided by VT, alpha IEQ by VT. Okay. Now, this inversion is an important aspect of the amplifier. So, that is why it is an inverting amplifier. That is why the gain is given as minus GM into RC, indicating a phase inversion of 180 degree. A sine wave of this type is going to appear as the sine wave of the other, right, with amplification. Now, as you go on increasing, let us now understand its behavior in the limiting range. This is going to be perfectly linear, and this factor can be used as long as we do not violate this too much. But the moment we start violating it, moment the input signal becomes of the order of let us say hundreds of millivolts, okay, then we can no longer use this information. It is not true that this is exact replica of this input waveform. It is not a sinusoid any longer. What happens? We would like to know, right, what happens. Now, we know that the diode characteristic is something like this. This is IE versus VBE, right, like this. What does it tell? As VBE is increased by a small amount, okay, the current increases by a huge amount. As VBE is increased by a small amount, okay, current increases by a huge amount on this side, whereas if VBE is decreased from this point, let us say this is VBEQ, this point is VBEQ. So, if I now increase VBE by some amount, this is the increase in current IE, whereas the decrease by the same amount, okay, is going to cause much less change in current. So, the increase in current is higher than the decrease in decrement in current. Increment in current is higher than the decrement in current because of the exponential relationship, which means that as this signal is applied, the emitter current is increasing here because VB is increasing, but the increment in current is going to be much more than the decrement. If the increment in current occurs, that causes decrease in voltage, right. So, for the same increase in voltage at the input, okay, there will be higher swing here than here. Is this point understood? This side, the voltage is going towards VCC, okay, maybe VCC may be somewhere here, okay, because current, if instantaneous value of current is decreasing, the voltage is therefore increasing, it is VCC minus something, right, IC times that. So, as IC increases, okay, or IE increases and IC increases, okay, the output voltage, okay, decreases, output voltage decreases. As IC decreases, okay, output voltage increases. So, this is going to be, okay, becoming flatter, and this is going to become longer. So, this is what you expect under linear behavior. Because of the nonlinear behavior, this is going to become flatter and this is going to become longer. This is because of the exponent nonlinearity. This is what exactly you will see on your oscilloscope. If you apply a signal at the input of a common emitter amplifier, this is going to become, okay, shorter, okay, and this is going to become longer. Is this distortion understood? This is one type of distortion which we have measured, okay, at low levels. We have measured this with the help of this equation. Other type of distortion which comes about, let it happen, we are not bothered, okay. What we will say is, I will still increase this input voltage Vp, I will keep on increasing. What will happen? This increase is going to occur, but it is disproportionate compared to this increase, right. So, for the next level, maybe this is the increase, okay, and here it may be only this, right. Is this clear? So, this kind of distortion will keep on happening until at a point this voltage V naught ultimately, okay, will reach at under the limiting situation of, this is nothing but, why is it decreasing or increasing? Because this current is changing from ICQ to ICQ plus IC, okay, which is a delta IC, okay. That delta IC can be positive or negative. That means instantaneous value of this current can be increasing above IEQ, ICQ, or decreasing, okay. When it is going on decreasing, it ultimately it can go to only 0, where ICQ minus ICQ this will become, okay. After which you cannot have further change in current because the transistor is off. Instantaneous value of emitter current is 0. Therefore, instantaneous value of collector current is 0, and therefore, the voltage here will reach VCC. So, this is what is going to happen ultimately. This here, it will be just a flat portion, because beyond that, okay, it cannot further increase. So, this point the transistor is set to go to cutoff. This is important that you remember what it is. The transistor is said to go to cutoff. This point, if you keep on increasing, what will happen? Let us see. As I keep on increasing this voltage, this current will keep on increasing. This voltage will keep on decreasing, because effective instantaneous value of current is increasing. This drop is going to decrease. So, this voltage will keep on decreasing, and it will reach a point when VCB is equal to 0. Thereafter, the transistor is said to go to saturation. Okay. So, instantaneous value of current IC equal to 0, cutoff, or actually speaking IE equal to 0, IC equal to 0, all are same. Instantaneous value of VBC equal to 0, saturation. So, after saturation, the transistor is not in the active region. So, this kind of what happens under saturation? This potential becomes same as this potential. There, after this junction starts getting forward biased, no longer will you have IC equal to alpha times IE. Transistor equation is not any longer valid. Okay. So, this entire transistor is now trying to become a short circuit. Okay. So, actually the inversion is lost. Okay. This point is going to be very nearly at the same point as this. If this voltage increases, this will also now increase. So, actually speaking, if it is not a large amplification, you will see that the input voltage will appear here increasing, right, because it is increasing at the input here. So, it will increase at the input until that saturation is reached. When this is increasing, this will be decreasing, right. So, how do you see saturation? Actually, if you magnify this point at this thing, it will look as though, right. So, it will, this portion, right, of the sine wave now, okay, will come here as such, right, because there is no phase inversion. Otherwise, it would have come as this, right. So, this will simply appear there. So, you can now distinguish between distortion occurring due to saturation, distortion occurring due to cutoff. These things are very clear. When it is cut off, right, it is just almost chopping off, because there is no voltage further increase that can occur, okay, just chopping off. When it is in saturation, it is not, right. This signal still appears, but its amplification factor is not at all there. It may appear just as such, okay, whereas this is the amplified signal. So, you might not really see that increase there, or it also might appear almost flat if it is a good amplifier. If it is a bad amplifier, you will clearly see that it has gone over to saturation, because there is going to be this flip over of this portion of the signal. Is it clear? Now, this is the saturation nonlinearity, this is the cutoff nonlinearity. Now, I want to make a very important thing clear here. The transistor, okay, amplifier is said to go to saturation in both these places, because it is not now any longer, okay, acting as an amplifier. The transistor amplifier is said to go to saturation, right. It is reaching its limiting level of output on either side. The transistor by itself may go to cutoff or saturation when the transistor amplifier goes to, okay, saturation. Is this clear? So, when you are considering amplifier, you will now bother about these points as saturation points, okay, where the amplifier characteristic will be just this. This is the linear characteristic, nonlinear. These are the two saturation levels. Okay. This, at this point, the transistor is going to saturation. At this point, the transistor has gone to cutoff. But as far as the amplifier itself is concerned, this whole thing is called saturation nonlinearity. Okay? Limiting nonlinearity it is called. Okay? So, this comprehensive thing is important in that in the initial stages, when these nonlinearities do not come into picture, when this system can be assumed to be linear, when this Vp is much less than 4 times Vt, then I can say that I will have one circuit for DC, another circuit separately for AC. Okay. This is VCC and there is no change here. At this point there is a change which is okay, V naught possible, because current IC is changing here and that is flowing through RC. So, for all changes increments in voltages, I am going to set up a separate equivalent circuit. For that purpose, wherever there is no change in voltage, that point is considered as ground point. Okay. No change in voltage with respect to common ground, that means it is the same as ground point. So, VCC is grounded, VE minus VE is grounded, okay. And for the equivalent circuit for this, now for only changes can be extracted from this. This RC is going to be grounded, grounded through capacitor CE, okay, and this is the this is the equivalent, okay, for only changes when the changes are small. Now, the transistor can be replaced by its equivalent circuit, linear equivalent circuit, where you are going to replace this by small Re, and this by alpha times IE when this current is IE. All these directions you must definitely put. So, this is valid all for only these signals Is. Okay. So, Vs is kept as such, Rs is kept as such, and through this Vs Rs combination, instead of IBQ plus Is flowing now, only Is will flow. Okay. So, through this only small Is will flow. Okay. Now, VCC is grounded, okay, and instead of through this, now ICQ plus IC flowing, only IC will flow, okay, instead of through this. Actually speaking, we will put it here, IE will flow, and this IE will flow not through this Re, but through this capacitor, which is a short circuit. Okay. So, basically speaking, therefore, this is going to be the equivalence, because the potential here remains constant, which is nothing but minus VEE plus IEQ into Re, constant potential, okay, if you have selected the capacitor properly. So, whenever there is a constant potential, we are grounding it.